Hello! This is the first in a series of very short videos on Strang chapters 4.3 and 4.4. I'm going to center on a problem in each video and talk you through it and talk the reasoning behind it. Talk about the reasoning behind it and give you some problems to practice on your own. So the first problem we're going to look at is fitting lines and curves to data. So let's say we have certain data points. Let's say we have these 4 data points. So when x is 2, we want an output of 3. When x is 3, we want an output of 2. When x is 5, we want an output of 1. When x is 6, we want an output of 0. So these are the data points we have, and we want to fit a line to it. So this is how we'll do that. First of all, we're going to set up a system of equations to solve. So here's our system of equations. This matrix times x1 and x2, 3, 2, 1, 0, represents, each of these rows represents an equation for a line. So we want x1 plus 2x2 to be equal to 3. So this is the line that would hold 2, 3 as a solution. This is the line that would pass through that. This is the line that would pass through the point 3, 2. This is the line that would pass through the point 5, 1. This is the line that would pass through the point 6, 0. So basically x1 is our y-intercept for our equation for our line, and x2 is the slope. And we want, ideally, all 4 points could be on one line, and these could all be satisfied. But in fact, if you do our usual routine on this augmented matrix, you're not going to get a solution. There is no solution. So if you go ahead and write the augmented matrix for this system and go ahead and do the row reduction, you're going to find that you're going to get a row with zeros, except in the last column, which is that augmented column, there's going to be an entry that's not 0, and that indicates no solution. Another way to say that is this b, where ax equals b, this is our a, this is our x, this is our b. This b is not in the column space of a. So in other words, we have b, I'm pretending this is our column space. I'm pretending it's a plane in the bottom there. B is not in that column space. So we can't find an x1 and an x2 that will map into that column space with this system. So what we do is we use projections. We say, okay, I'm going to project B onto the column space of A. And that's going to give me the vector ax hat, where x hat is something in our original space. So x hat is something in R2 that we want to map into the column space of A. But obviously this one won't map into the column space of A. So we have to find one that'll map into the column space of A. And the one we want, the one that's closest to B in a least square sense, that is in a Euclidean sense, is the one that we get when we drop a perpendicular from B down to the column space of A. Okay, so to get that, we know the equations. So we know that since this error, B minus AX hat, is in the null space of A transpose, then we know that this has to be true. A transpose AX hat has to be equal to A transpose B. Okay, so that's what we have to solve to get X hat. So we're getting something in R2 that when we apply A to it will map into the column space. So we're looking for something where B, we're changing B, we're making a new B that's going to be in the column space of A. So now we have, here's A transpose, here's A. I put a little hat on the x1 and the x2. Here's A transpose, here's B. So rather than getting a projection matrix like we often did before, I just want to write these out and solve for x hat. So I go ahead and multiply A transpose A and I get that. I go ahead and multiply A transpose B and I get that. So go through the usual routine, and our solution is x1 hat is 4.3, x2 hat is negative 0.7. Okay, that's our line. Our line of best fit, that is the closest we can get to those four data points, is going to be, so this one is the y-intercept, this one is the slope. So it's going to be y equals, our solution is y equals negative 0.7x plus 4.3. So that's our line. But if we put in an x of 2, well, we're not going to get out 3, we're going to get out something close to 3. If we put in an x of 3, we're not going to get out 2, we're going to get out hopefully something close to 2. To find out how close our line is, we look at this error. That's this line here. And our error turns out to be this vector. That's our error vector. So what we're doing is we're using projection to get the closest we can to something in the column space of A, so that this system does have a solution. Okay, I'll see you next time.